Chapter 3, Atoms and Molecules, Class 9th Science, CBSE based. Topics from syllabus: Atoms and Molecules, Law of Chemical Combination, Chemical Formula of Common Compounds, Atomic and Molecular Masses. Introduction to Chemical Reactions and Laws of Chemical Combination. Chemical reactions occur when two or more substances combine to form new products. These reactions are governed by specific rules called the laws of chemical combination. Two of the most important laws are: Law of Conservation of Mass. This law states that mass can neither be created nor destroyed. In a chemical reaction, the total mass of the reactants is always equal to the total mass of the products. Example: in a reaction between 5.3 grams of sodium carbonate and 6 grams of ethanoic acid, the products formed are 2.2 grams of carbon dioxide, 0.9 grams of water, and 8.2 grams of sodium ethanoate. Reactants: sodium carbonate is equal to 5.3 g and ethanoic acid is equal to 6 g. Total mass of reactants is equal to 5.3 plus 6 is equal to 11.3 g. Products: carbon dioxide is equal to 2.2 g, water is equal to 0.9 g and sodium ethanoate is equal to 8.2 g. Total mass of products is equal to 2.2 plus 0.9 plus 8.2 is equal to 11.3 g. The total mass of the reactants equals the total mass of the products, proving the law of conservation of mass. Law of constant proportion. This law states that a pure chemical compound always contains the same elements in the same proportion by mass, no matter where it is found or how it was created. Example: water is always made of hydrogen and oxygen in the ratio of 1:8 by mass. If you have 3 grams of hydrogen gas, the mass of oxygen needed to react with it will be hydrogen 1 part and oxygen 8 parts. Therefore, to react with 3 g of hydrogen, oxygen required is equal to 3 times 8 is equal to 24 g. Question: a 0.24 g sample of compound of oxygen and boron was found by analysis to contain 0.096 g of boron and 0.144 g of oxygen. Calculate the percentage composition of the compound by weight. Solution. Step 1. Write down the mass of each element. We are given mass of boron, B, is equal to 0.096 g. Mass of oxygen, O, is equal to 0.144 g. Total mass of the compound is equal to 0.24 g. Step 2. Calculate the percentage composition of boron. To find the percentage composition of boron, use the formula. Percentage of boron is equal to mass of boron over denominator, total, mass of the compound and denominator, times 100. Substitute the values. Percentage of boron is equal to 0.096 over 0.24 times 100. Percentage of boron is equal to 0.40 times 100 equals 40%. Step 3. Calculate the percentage composition of oxygen. Similarly, to find the percentage composition of oxygen, use the same formula. Percentage of oxygen is equal to mass of oxygen over denominator, total, mass of the compound and denominator, times 100. Substitute the values. Percentage of oxygen is equal to 0.144 over 0.24 times 100. Percentage of boron is equal to 0.60 times 100 equals 60%. Step 4. Summarize the results. The percentage composition of the compound by weight is: boron 40% and oxygen 60%. Thus, the compound contains 40% boron and 60% oxygen by weight. Question: when 3.0 g of carbon is burned in 8.00 g oxygen, 11.00 g of carbon dioxide is produced. What mass of carbon dioxide will be formed when 3.00 g of carbon is burned in 50.00 g of oxygen? Which law of chemical combination will govern your answer? Solution. This problem is governed by the law of constant proportion, which states that a chemical compound always contains its constituent elements in the same proportion by mass, regardless of the amount of reactants or their source. Step 1. Understanding the reaction. The chemical reaction involved is the combustion of carbon in oxygen, which produces carbon dioxide. Carbon plus oxygen, carbon dioxide. Step 2. Given data. When 3.0 g of carbon reacts with 8.0 g of oxygen, 11.0 g of carbon dioxide is produced. The reaction follows the law of constant proportion, meaning a fixed amount of carbon always reacts with a fixed amount of oxygen. Step 3. Applying the law of constant proportion. The key information from the reaction is that 3.0 g of carbon plus 8.0 g of oxygen when 1.0 g of carbon dioxide. This tells us that 3.0 g of carbon always reacts with 8.0 g of oxygen to produce 11.0 g of carbon dioxide. Step 4. New situation with excess oxygen. Now, we are asked to find the mass of carbon dioxide produced when 3.0 g of carbon is burned in 50.0 g of oxygen. According to the law of constant proportion, 3.0 g of carbon will still only react with 8.0 g of oxygen. The remaining oxygen will be unreacted. Step 5. Calculating the mass of unreacted oxygen. If 50.0 g of oxygen is initially present and only 8.0 g is used in the reaction, the excess oxygen can be calculated as Excess oxygen is equal to 50.0 G, 8.0 G is equal to 42.0 G. So, 42.0 G of oxygen will remain unreacted. Step 6. Mass of carbon dioxide produced. Since the same amounts of carbon, 3.0 G, and oxygen, 8.0 G, react as in the original situation, the amount of carbon dioxide produced will be the same. Mass of carbon dioxide is equal to 11.0 G. Step 7. Conclusion. The mass of carbon dioxide formed will still be 11.0 G. The 42.0 G of oxygen will remain unreacted. This result is governed by the law of constant proportion, which states that a chemical compound always contains the same elements in the same ratio by mass. Thus, even with excess oxygen, the reaction uses only 8.0 G of oxygen for every 3.0 G of carbon, and the remaining oxygen stays unreacted. Dalton's atomic theory. John Dalton proposed a theory to explain these laws. All matter is made up of tiny particles called atoms. Atoms cannot be created or destroyed in a chemical reaction. This supports the law of conservation of mass. Atoms of the same element have the same mass and properties. Atoms of different elements have different masses and properties. Atoms combine in whole numbers to form compounds. This supports the law of constant proportion. Drawbacks of Dalton's atomic theory. While Dalton's atomic theory was groundbreaking in explaining the laws of chemical combination, it had certain limitations that were revealed with further scientific discoveries. Some of the major drawbacks of Dalton's atomic theory are: indivisibility of atoms. Dalton's claim. Dalton proposed that atoms are indivisible and cannot be broken down further. Modern understanding. Later discoveries, such as the discovery of subatomic particles, electrons, protons, and neutrons, proved that atoms are divisible and consist of smaller particles. No explanation for isotopes. Dalton's claim. Dalton assumed that all atoms of an element have identical mass. Modern understanding. Isotopes of an element were discovered, which are atoms of the same element having different masses but similar chemical properties. For example, chlorine has two isotopes, chlorine-35 and chlorine-37. No explanation for allotropes. Dalton's claim. According to Dalton, all atoms of an element have the same properties. Modern understanding. Allotropes, such as diamond and graphite, both forms of carbon, show different physical properties despite being made of the same element, carbon. What is an atom? An atom is the smallest particle of an element that takes part in chemical reactions. Atoms maintain their identity during chemical changes and cannot be broken down further by chemical means. Size of atoms. The size of atoms is extremely small. For example, the atomic radius of a hydrogen atom is approximately 0.037 nanometers, nm. How is atomic radius measured? Atomic radius is measured in nanometers, nm. A nanometer, nm, is a unit of length in the metric system, and it is equivalent to 1 nm is equal to power of 10 is 9 meters. For example, if the atomic radius of hydrogen is 0.037 nm, this can be expressed as 0.037 times power of 10 is 9 meters. Symbols of atoms. Dalton was the first scientist to introduce symbols to represent elements in a specific way. When he used a symbol, like a circle for hydrogen or oxygen, it didn't just represent the element itself, it also stood for one atom of that element. So, each symbol meant a definite, individual quantity of the element. Later, another scientist named Berzelius came up with an easier and more practical system. He suggested using one or two letters from the element's name as its symbol. For example, the International Union of Pure and Applied Chemistry, IUPAC, assigns symbols to elements. For example, modern symbols of elements. In modern chemistry, symbols for elements are based on one or two letters of the element's name, often derived from either their English or Latin names. These symbols were introduced by Johannes Jakob Berzelius in the early 19th century and are universally accepted today. Each element's symbol consists of one capital letter, O, a capital letter followed by a lowercase letter. Why use symbols? Simplicity. Instead of writing the entire name of the element, we use symbols to quickly and clearly identify them. Universal understanding. Chemical symbols are the same across all languages and countries, which allows scientists to communicate easily. Examples of modern element symbols. Element. Symbol. Explanation. Hydrogen. First letter of its English name. Helium. First two letters of its English name. Oxygen. First letter of its English name. Carbon. First letter of its English name. Nitrogen. First letter of its English name. Sodium. From the Latin name natrium. Potassium. From the Latin name kalium. Iron. From the Latin name ferrum. Gold. From the Latin name aurum. Silver. From the Latin name argentum. Mercury. From the Latin name hydrargyrum. Lead. From the Latin name plumbum. Copper. From the Latin name cuprum. Calcium. First two letters of its English name. Aluminium. First two letters of its English name. Zinc. First two letters of its English name. Chlorine. First two letters of its English name. Phosphorus. First letter of its English name. Sulfur. First letter of its English name. Rules for symbols. The first letter is always capitalized. If there is a second letter, it is always in lowercase. Symbols are usually derived from either the first letters of their name or their Latin name. Why some symbols seem unrelated to their English names? Some elements have symbols that come from their Latin names instead of English names to avoid confusion with other elements. For example, these days, the names and symbols of all newly discovered elements are approved by the International Union of Pure and Applied Chemistry, IUPAC. Atomic mass. Introduction to atomic mass. The concept of atomic mass is a fundamental part of Dalton's atomic theory. Dalton proposed that each element has a specific atomic mass, which helps explain how elements combine in fixed proportions to form compounds. This idea supports the law of constant proportions, which states that a chemical compound always contains the same elements in the same ratio by mass. Understanding atomic mass. Atomic mass unit, U. The atomic mass of an element is measured in atomic mass units, formerly abbreviated as AMU, now written as U. One atomic mass unit is defined as 1/12th of the mass of a carbon-12 atom. Determining relative atomic masses. Since it is challenging to measure the mass of individual atoms directly, scientists determine relative atomic masses by examining how elements combine in chemical reactions. Example: carbon monoxide. In a reaction, 3G of carbon combines with 4G of oxygen to form carbon monoxide. This means carbon combines with 4/3 times its mass of oxygen. If we define the mass of a carbon atom as 1.0 U, we can assign a relative atomic mass to oxygen. The initial approach. Initially, scientists considered using 1/16 of the mass of an oxygen atom as the atomic mass unit because oxygen reacts with many elements and forms various compounds. Using this scale resulted in atomic masses of many elements being close to whole numbers. Adoption of carbon-12. In 1961, scientists agreed to use the carbon-12 isotope as the standard for measuring atomic masses. This means 1 atomic mass unit, U, is equal to exactly 1/12 of the mass of one carbon-12 atom. As a result, the relative atomic masses of all elements are now calculated based on this standard. How atoms exist. Atoms of most elements do not exist freely in nature, instead, they combine to form molecules, groups of two or more atoms bonded together. For example, a water molecule consists of 2 hydrogen atoms and 1 oxygen atom. Ions, atoms that have gained or lost electrons and carry a charge, such as sodium ion or chloride ion. These molecules and ions come together in large numbers to form the matter we can see, feel, or touch. The atomic mass of an element is the mass of one of its atoms. The atomic mass unit, AMU, is used to measure it. 1 AMU is equal to open parent 1/12 close parent th, the mass of a carbon-12 atom. Molecules, how atoms exist. Atoms of most elements are too reactive to exist alone and combine to form molecules or ions. Noble gases, like helium, neon, exist as single atoms because they are stable. A molecule is a group of 2 or more atoms bonded together and can exist independently. Molecules. Molecules are groups of 2 or more atoms bonded together. They can either consist of the same type of atoms, molecules of elements, or different types of atoms, molecules of compounds. Molecules of elements. A molecule of an element is made up of 2 or more atoms of the same element chemically bonded together. Examples. Oxygen, a molecule of oxygen has 2 oxygen atoms. Nitrogen, a molecule of nitrogen has 2 nitrogen atoms. Hydrogen, a molecule of hydrogen has 2 hydrogen atoms. Key point, molecules of elements contain only one type of atom. Molecules of compounds. A molecule of a compound is formed when atoms of different elements bond together. Examples. Water, a water molecule is made of 2 hydrogen atoms and 1 oxygen atom. Carbon dioxide, a carbon dioxide molecule consists of 1 carbon atom and 2 oxygen atoms. Key point, molecules of compounds contain 2 or more different types of atoms. Chemical formulae. The chemical formula of a substance tells us the types and numbers of atoms present in one molecule of that substance. Formulae of elements. For elements that exist as molecules, their chemical formula reflects the number of atoms bonded together. Examples. Oxygen, 2 oxygen atoms. Nitrogen, 2 nitrogen atoms. Sulfur, 8 sulfur atoms. Rules for writing chemical formulae. Write the symbols of the elements. Write the valency of each element below its symbol. Cross over the valencies to form the formula. Examples. For calcium oxide. Calcium has a valency of 2, oxygen, O, has a valency of 2. Formula is equal to. Read the table below. Formulae of compounds. The chemical formula of a compound shows the types and proportions of atoms that make up one molecule of that compound. Examples. Water, the formula shows 2 hydrogen, H, atoms and 1 oxygen, O, atom. Carbon dioxide, the formula shows 1 carbon, C, atom and 2 oxygen, O, atoms. Sodium chloride, the formula shows 1 sodium atom and 1 chlorine atom. Key point, the chemical formula tells us how many atoms of each element are present in a molecule. Molecular mass. The molecular mass of a substance is the sum of the atomic masses of all atoms present in a molecule of the substance. It is measured in atomic mass units, U or AMU. Steps to calculate molecular mass. Write the chemical formula of the molecule. Find the atomic mass of each element in the molecule. Refer to the periodic table for atomic masses. Multiply the atomic mass by the number of atoms of that element in the molecule. Add the total masses of all the elements to get the molecular mass. Example 1, water. Atomic mass of hydrogen, H, is equal to 1 U. Atomic mass of oxygen, O, is equal to 16 U. In one molecule of water, there are 2 hydrogen atoms and 1 oxygen atom. So, molecular mass of water is equal to 2 times 1 U plus 1 times 16 U is equal to 2 U plus 16 U is equal to 18 U. Example 2, carbon dioxide. Atomic mass of carbon, C, is equal to 12 U. Atomic mass of oxygen, O, is equal to 16 U. In one molecule of carbon dioxide, there is 1 carbon atom and 2 oxygen atoms. So, molecular mass of carbon dioxide is equal to 1 times 12 U plus 2 times 16 U is equal to 12 U plus 32 U is equal to 44 U. Key point, molecular mass is the sum of the atomic masses of all atoms in the molecule. Atomicity. Atomicity refers to the number of atoms in a molecule of an element. Examples. Argon is monoatomic, 1 atom per molecule. Oxygen is diatomic, 2 atoms per molecule. Ozone is triatomic, 3 atoms per molecule. Phosphorus is tetraatomic, 4 atoms per molecule. Sulfur is octatomic, 8 atoms per molecule. Ions. What are ions? Ions are atoms or groups of atoms that have gained or lost electrons, resulting in a net electric charge. This charge can be positive or negative depending on whether electrons are lost or gained. Ion formation. Losing electrons. When an atom loses one or more electrons, it becomes a positively charged ion called a cation. Gaining electrons. When an atom gains one or more electrons, it becomes a negatively charged ion called an anion. Positively charged ions, cations. Cations are ions with a positive charge. They are formed when atoms lose electrons. Characteristics of cations. Typically formed by metals. Have fewer electrons than protons. Examples include sodium ion, calcium ion, and iron ion. Examples of cations. Sodium ion. Formation. Sodium loses one electron. Symbol. Sodium ion. Charge. +1. Calcium ion. Formation. Calcium loses 2 electrons. Symbol. Calcium ion. Charge. +2. Iron ion. Formation. Iron loses 3 electrons. Symbol. Iron ion. Charge. +3. Key point. Cations are formed by metals losing electrons and carry a positive charge. Negatively charged ions, anions. Anions are ions with a negative charge. They are formed when atoms gain electrons. Characteristics of anions. Typically formed by nonmetals. Have more electrons than protons. Examples include chloride ion, oxide ion, and nitride ion. Examples of anions. Chloride ion. Formation. Chlorine gains 1 electron. Symbol. Chloride ion. Charge. 1. Oxide ion. Formation. Oxygen, O, gains 2 electrons. Symbol. Oxide ion. Charge. 2. Nitride ion. Formation. Nitrogen, N, gains 3 electrons. Symbol. Nitride ion. Charge. 3. Key point. Anions are formed by nonmetals gaining electrons and carry a negative charge. simple ions and compound ions, polyatomic ions. Simple ions, monatomic ions. Simple ions consist of a single atom that has gained or lost electrons to form a charged particle. Examples: sodium ion, chloride ion, calcium ion, sulfide ion. Compound ions, polyatomic ions. Compound ions, also known as polyatomic ions, consist of two or more atoms bonded together that function as a single charged entity. Characteristics of polyatomic ions: contain both metals and nonmetals or multiple nonmetals. Have a specific ratio of atoms. Possess an overall charge. Science class 9th.